These are Arabic numerals. But incidentally, Newton made his proof geometrical like this, and made all his proofs in his book geometrical of this type. Today we don't use that kind of reasoning. We use a kind of analytic reasoning with symbols, which this kind of reasoning requires an ingenuity to draw the right triangles, the correct triangles, I mean, to notice about the areas and to figure out how to do it. You have to be clever. But there have been improvements in the methods of analysis so that one can be quite more stupid. And I write much faster, you're much more efficient then. And I want only to show what it looks like in the notation of the more modern mathematics, where you don't do anything but write a lot of symbols to figure it out. First, we would like to talk about how fast the area changes, and we represent that by area dot. And the area changes because of when the radius is swinging, it's the component of velocity at right angles to the radius times the radius that tells how fast the area changes. So this is the component of the radial distance multiplied by the velocity or rate of change of the distance. Now the question is whether the rate of change of area itself changes. The principle is it's not supposed to change. The rate of change of area is not supposed to change. So we differentiate, so-called, this again, and we put, that'll mean some little trick about putting dots in the right place. And that's all. You have to learn the tricks. It's just a series of rules that people have found out that are very powerful for such a thing. And this says the component of the velocity at right angles to the velocity. It is none. There is none. The velocity is in the same direction as itself. And the acceleration, which is this thing, the second derivative, or the derivative of velocity, is the force divided by the mass. So this says that the rate of change of the area is the component of force at right angles to the radius. But if the force is in the direction of the radius, as Newton said, then there's no force at right angles to the radius, and that means that the rate of change of area doesn't change. I just wanted to illustrate the different kinds of notation. Now, Newton knew how to do this, more or less, with slight different notations, but he wrote everything this way because he tried to make it possible for people to read his papers. He invented the calculus, which is this kind of mathematics, and is a good illustration of the relation of mathematics to physics. When the problems in physics get difficult, we may often look to the mathematicians who have already studied such a thing and have reasoned about such an item before and have prepared a line of reasoning for us to follow. On the other hand, they may not have, in which case we have to invent our own line of reasoning, which will then pass back to the mathematicians, because everybody who reasons carefully about anything is making a contribution to the knowledge of what happens when you think about something. And if you abstract it away and send it to the Department of Mathematics, they put it in the books as a branch of mathematics. Mathematics, then, is a way of going from one set of statements to another. It's evidently useful in physics because we have all these different ways that we can speak of things, and it permits us to develop consequences and analyze the situations and change the laws in different ways and to connect all the various statements. So that, as a matter of fact, the total amount that a physicist knows is very little. He has only to remember the rules for getting from one place to another, and he's able to do it then. In other words, all of the various statements about equal times, the forces in a direction of the radius, and so on, are all interconnected by reasoning. Now an interesting question comes up. Is there some pattern to it? Is there a place to begin fundamental principles and deduce the whole works? Or is there some particular pattern or order in nature in which we can understand that these are more fundamental statements and these are more consequential statements? There are two kinds of ways of looking at mathematics, which for the purpose of this lecture I will call the Babylonian tradition and the Greek tradition. In Babylonian schools in mathematics, the student would learn something by doing a large number of examples until he caught on to the general rule. Also, a large amount of geometry, for example, was known. A lot of properties of circles, theorem of Pythagoras, for example, formulas for the areas of cubes and triangles and everything else. And some degree of argument was available to go from one thing to another. Tables of numerical quantities were available so that you could solve elaborate equations and so on. Everything was prepared for calculating things out. But Euclid discovered that there was a way in which all of the theorems of geometry could be ordered from a set of axioms that were particularly simple, and you're all familiar with that much geometry, I'm sure. But the Babylonian attitude was, if I make my way of talking, what I call Babylonian mathematics, is that you know all these various theorems and many of the connections in between, but you've never really realized that it could all come up from a bunch of axioms. Modern mathematics, the most modern mathematics, concentrates on axioms and demonstrations within a very definite framework of conventions of what's acceptable and not acceptable as axioms. For example, in geometry, to take something like Euclid's axioms modified to be made more perfect and then to show the deduction of the system. For instance, it would not be expected that a theorem like Pythagoras' that the sum of the squares of the areas of squares put on the sides of the triangle will equal the area of a square on a hypotenuse should be an axiom. On the other hand, from another point of view of geometry, that of Descartes, the Pythagorean theorem is an axiom. So the first thing we have to worry about is that even in mathematics, you can start in different places. Because of all these various theorems are interconnected by reasoning, there isn't any real way to say, well, these on the bottom here are the bottom, and these are connected through logic. Because if you were told this one instead, or this one, you could also run the logic the other way if you weren't told that one, and work out that one. It's like a bridge with lots of members, and it's over-connected. If pieces have dropped out, you can reconnect it another way. The mathematical tradition of today is to start with some particular ones which are chosen by some kind of convention to be axioms and then to build up the structure from there. The Babylonian thing that I'm talking about, which I don't really not Babylonian, but is to say, well, I happen to know this and I happen to know that and maybe I know that and I work everything out from there. And tomorrow I forgot that this was true, but I remembered that this was true and then I reconstruct it again and so on. I'm never quite sure of where I'm supposed to begin and where I'm supposed to end. I just remember enough all the time so that as the memory fades and the pieces fall out, I put the thing back together again every day. The method of starting from the axioms is not efficient in obtaining the theorems. In working something out in geometry, you're not very efficient if each time you have to start back at the axioms. But if you have to remember a few things in the geometry, you can always get somewhere else. It's much more efficient to do it the other way. And what the best axioms are not exactly the same, in fact are not ever the same, as the most efficient way of getting around in the territory. In physics, we need the Babylonian method and not the Euclidean or Greek method, and I would like to say why. The problem in the Euclidean method is to make something about the axioms a little bit more interesting or important. But the question that we have is, in the case of gravitation, is it more important, is it more basic, is it more fundamental, is it a better axiom to say that the force is directed toward the sun, or to say that equal areas are swept in equal time? Well, from one point of view, the forces is better, because if I state what the forces are, I can deal with a system with many particles in which the orbits are no longer ellipses because of the pull of one on the other, and the theorem about equal areas fails. Therefore, I think that the force law ought to be an axiom instead of the other. On the other hand, the principle that equal times are swept out in equal areas are swept out in equal times can be generalized when there's a system of a large number of particles to another theorem, which I had prepared to explain, but I see I'm running out of time. But there's another statement which is a little more general than equal areas in equal time. Well, I have to state what it is. It's rather complicated to say, and it's not quite as pretty as this one, but it's obviously the son of this one. I mean, it's the